1 gigahertz to 2 gigahertz, it is also okay. But after that, because it is a counter, when it counts, for example, it is counting to 00 to 01, then 10, then 11. After that, again, it will come to 00, right? Which means after 2 gigahertz, it will again come back to 250 megahertz, and that is not allowed. The moment it reaches 2 gigahertz, it should lock there. For locking, they have used another multiplexer, and this particular multiplexer is controlled by another secondary clock. Another secondary clock where they have designed some unit step function generator by which they have stabilized it. Now there is a basic problem in this particular circuit also. First basic problem is generation of clock through quartz crystal is itself challenging. But if you need another secondary clock, it doesn't make sense. Okay. So requirement of two clocks are there. Here you have a high frequency clock, here it is a secondary clock. So the requirement of secondary clock is redundant. Means if a proper circuit improvisation is done or if a proper research is done, this secondary clock has to be eliminated. Then the circuit will be more real. Okay. This was one problem in this circuit. And the second problem is noted that in the IBM work, they have followed the IBM work. But in the IBM work, I have mentioned that the minimum frequency ramp which they have achieved was 17.5 megahertz per microsecond. These work, they were least bothered about the frequency ramp. They did not even analyze what is the frequency ramp. And the moment we estimated the frequency ramp, we have found that the estimated frequency ramp is much higher than what IBM has proposed. So it is of no use. Architecturally, they are better. They are getting also VFC, but the objective, the reason for which VFC is generated, that is not solved. That is not sustained. Okay. So considering this problem, we have improvised this particular design only. Right? This particular design itself was accepted in IEEE transaction. So we have basically understood what is available in the literature and we thought of a particular plan. Right? Now see, the plan was, because the core is working in the 2 gigahertz, right? What we have done, and we know that the base clock is somewhere around 120 to 130, right? I have mentioned you. See, I have written here, it is 133 megahertz as per the datasheet of Intel. So for our research, we have considered the base clock as a 125 megahertz. This frequency, 125 megahertz we have chosen. After that, we have used some divider to generate some more frequencies like 62.5, 31.25, 15.625. We have used using divider. And we have used some multiplier by which we have generated 250, 500, 1 gigahertz and 2 gigahertz. Okay. So multiplier and divider has been used. This is the plan and this is the more precise diagram, the way it will look. Initially see time period is large, which is frequency is less. And at last, time period is almost not visible, which means frequency is extremely high. Okay. And it was the actual architecture. This is the base clock, which is 125. Okay. It is given to this particular marks. 125 is also given to some multiplier circuit from which we are generating the 250, 500, 1 gigahertz and 2 gigahertz. And then we have many number of divisions. Okay. And these divisions are given to this particular marks and few divisions are coming to another marks which we have built. We have built a different marks also, and we have also built a control logic for automation of the select line of the first blue color marks. Okay, because objective is what? Initially there was a secondary clock and we mentioned that the secondary clock cannot be used. Right? So to automate it, we have built a control logic. So what will happen? The control logic will work. In the control logic, we have used a down counter, a 3-bit down counter, because here we have used a 8:1 marks. 8:1 marks means 3 select lines will be needed. So 3 select lines will come out from 3 flip-flops, and using 3 flip-flop, we can build a 3-bit counter, right? So how the 3-bit counter will count? We have built a down counter, so it will count from 111, then 110, 101 like this to 000. And we have built in such a way that the moment the control logic will generate 000, the counter will stop functioning automatically and it will lock at 000. And the marks is built in such a way that at 111, lowest frequency will be sent at the output. At 110, the next higher frequency will be sent. At 101, next higher frequency will be sent, like this. Okay? So down counting is happening, and at the output, frequency is rising. And the moment it will be at 000, you will get 2 gigahertz at the VFC, and because 0 is getting locked at the output of control logic, your blue color marks is also locked at 000 in the select line. And at the output, always you are going to get 2 gigahertz. Okay, so this is how the automation is achieved comparing to the previous circuit. I think these are certain data. This is about when we have built the flip-flop. We did not use the conventional, architecture of the flip-flop. This is a new flip-flop we have designed. This is also a part of our research. And then using our proposed flip-flop only, we have built that master slave architecture using the T flip-flop for the frequency division. And these are the data of the frequency divisions which we have used. This sort of frequency division we have done, and this phone number of multiplication we have done. These are just data. Okay, out of which these 4 are going as an input to the blue color marks. These 3 are also going as an input to the blue color marks, and 125 megahertz was a base frequency which is also going to the blue color marks. And all these blue color frequency division, they are input to this secondary marks. What this secondary marks is doing? This secondary marks is giving the input frequency to this control logic. I mentioned that what is a control logic? Control logic is nothing but a down counter, right? So down counter also has to run at a frequency. So we are giving frequency. So whatever frequency is needed, we can select, and that frequency is given to the control logic. That's the thing. And this is the actual architecture of the control logic. The control logic I mentioned, and this is the architecture of the control logic. Okay. Internally, you can see how we have done in the control logic, I mentioned that it is a down counter. No. Internally, every flip-flop is getting input through another 2:1 marks. Here also 2:1 marks, here also 2:1 marks, here also 2:1 marks. What we are doing basically is, see, in these 2:1 marks, one input is coming from Q, another input is coming from Q bar. Okay. So when it will come from Q bar, frequency division will happen, means the counting will happen. The moment Q will get connected to the input, you will get locked, isn't it? Because if Q is going at the input, that input will again come as an output, isn't it? So if at the output 000 is coming, and if it is rotating as an input, so always you will get 000, and the system will be locked, right? So that is the operation. At all combination, this is just for operation. At all combination, see, if you get 1000 at the output, if 100, they are connected to an OR gate, output will be 1. If the output is 1, all the ones are going to the all 2:1 marks. So this one input will be selected. If this one input is selected, you see 1 is coming from Q bar, means it will allow down counting. So starting from 111 to 110, 101 till 001, every time the OR gate will generate a logic 1, And because the OR gate is generated logic 1, this 2:1 marks is always getting 1 in the select line. So always Q bar is getting connected as an input. Only the time it will be all 0, 0, 0, all three are 0, your OR gate output will be 0. The moment OR gate output is 0, you are giving 0 at the input of all the 2:1 marks. The moment input is settled at 0, what will happen? Now Q bar is not coming. Q is going as an input. At each flip-flop, Q is going at the input. Here also Q is going at the input. Now what will happen if Q goes, whatever may be the number of clock hitting you give, it will always get locked at 0, 0, 0, right? So this is the internal circuit we have built. This is the entire layout of the design which we have done in the 65 nanometer. Anyway, so see, we have estimated at every combination. See, this is P2, P1, P0. What is the P2, P1, P0? You can come to this circuit, the bigger circuit. You see P2, P1, P0 is coming from here. This is the select line of the secondary marks. So depending on this secondary mark, depending on this P2, P1, P0, you can decide which frequency is going to work as a clock of the control logic, right? And this will decide what is going to be the wake up time of the VFC. What is the wake up time? Wake up time is the time needed from the lowest frequency to reach the highest frequency. That is wake up time. See, in this graph, we have discussed the wake up time. From here till here, at this particular instance, we have reached the 0, 0, 0 at the output of the control logic. 0, 0, 0 we have reached, means we have reached the 2 gigahertz at the output, right? So this is the wake up time. So if you change the input frequency of the control logic, the wake up time will also vary. And the more wake up time you will give, the lesser DIDT you are going to get, or lesser frequency ramp you are going to get, right? So that's what we have seen at 0, 0, 0, at 0, 0, 1, different frequencies going, and see what we have achieved. At 110, we have achieved a frequency ramp of 17.3023 megahertz per microsecond, which is close to the data of the IBM TJ Watson Research Center. And 111 condition, we have achieved a frequency ramp which is lower than what IBM has promised, right? And we know the lower we can make, the better it for the DIDT, because DIDT will reduce. Okay. And thereafter in the research, we mentioned, we have done a clock gating using the lector, which we have discussed earlier. And this entire architecture is the generation of the VFC. So VFC itself is giving betterment comparing to the conventional clock. And then VFC is given to the clock gating circuit. And then finally, we are testing it on some application, right? Some bigger applications. So, and accordingly, we have tested the data that what is the performance is looking like. Okay. This is actually the current profile. I mentioned that fundamentally we analyze the DC current, but current profile means instantaneously how current profile is. Now, this current profile is when we are giving a conventional 2 gigahertz clock. So in the system, in our testing system, we have given 2 gigahertz conventional clock. And this is the fluctuation. And you see, I mean, this is quite dense, so I cannot zoom and show. But see the density. The fluctuation is not even visible. And see here, in this particular architecture, where it is driven by the VFC. You see, in the left-hand side, the current density is lesser. In the right hand side, current density is slightly higher because in the left hand side frequency was 62.5 megahertz, right hand side frequency jumped to 125 megahertz. Now when it will jump from 125 to 250, current density will be slightly more. 250 to 500, current density will be comparatively more, right? Like this, current density will increase. And this is the final current profile when we have tested it by connecting variable frequency clock and also the new clock getting technology. Now you can see how lightly dense it is. You see this one, highly dense, right? The same circuit is tested VFC plus LCD-CG. Density of the current with respect to time has reduced. So definitely your DIDT and IT will also, average IT will also get reduced. And because in the first time, I mean, in the starting of the lecture, we mentioned as a circuit designer, our role is to play with the IT and DIDT, right? So the impact will come there. Impact will come at the IT and DIDT. These are anyway some data. I don't want to, go into much into the detail. You can see here for a circuit, this circuit, when we have tested, you can see the power component. Using the conventional clock, power was, I think, 4.1 microwatt. Using VFC, it is 3.7 microwatt. Using VFC plus LCD-CG, you can see how lesser it is. It has gone to nanowatt, 0.0007 microwatt. So it is 0.7 nanowatt. That small it has become. Okay. So in the PSN also you can check. In the PSN, initially PSN was 0.112 volt. After connecting the LCD-CG and the VFC, you see how lesser it is. It has gone to picovolt. It is that small, 20 picovolt it has gone. Okay. So these are some analysis. Again, we have analyzed in different process voltage and temperature. I'm skipping these sections. This is some data I can show you. We have tested our circuit in some real benchmark circuit of ISCAS 89 and ITC. You can see the values here. These peaks, all these peaks are in terms of conventional. Any bigger, you can think of this color. Here, the PSN is 5.9 microvolt, right? With VFC, it has reduced to 5.6 here. And the same, when we have incorporated clock getting and VFC, it has reached to 1.3. Average power also you can check. For the same circuit, it was 216 microwatt for a bigger circuit. It has reduced to 208 microwatt when VFC has been incorporated. With VFC plus clock getting, it has come down to only 49.764 microwatt. Now, these are all small circuit or small benchmark circuit. Finally, we have tested it in a bigger benchmark circuit. A bigger benchmark circuit with you can see that in this circuit, average power was 4,550 milliwatt, and it has come down to almost half to 304 milliwatt. It is in the range of milliwatt, right? So current is quite large. So that kind of beneficial you are going to get if you incorporate clock getting along with the VFC or variable frequency clock. These are some generic projection we have done out of all the testing. We have done a projection that power and PSN will be reduced if the number of modules in the systems are large, and this reduction will be comparatively more. I mean, if sequential number of sequential elements are also more, means in a system, if the number of sequential elements are more, then the percentage reduction of power and PSN will also be more if we use this kind of concept of integrating VFC and VFC plus clock getting. These are the few team members who, this is actually a big project. This is a project which is granted by SERB CRG. These are few of my students who worked in this particular entire project. They are all, settled in their, in life, but there are quite a few research still left in this particular domain itself, which I don't want to discuss much, but I want to show just one thing, that see this architecture. When I talk about clock, no, clock is generated by a PLL, for example, but there is a clock distribution network. You see how clock distribution happens. Clock distribution happens through some chain of inverters. And inverters are practically very much prone to the short circuit power dissipation. In the higher frequency, short circuit power is huge in inverters. In all sorts of clock distribution, internally, whatever you have nothing but inverter change. Everywhere, in all sorts of clock distribution techniques, you have nothing but inverter, right? Everywhere, in Pentium 4 processor, dual core processor, Intel i7, i5, i3, everywhere they have used inverters only, right? So what we can think of is, we can think of modifying this inverter series using some inverter which will be controlled inverter. Controlled inverter means the inverter should turn on by itself only when it is needed to turn on. So can we do something like that? So there are a lot of research possible by which this PSN power supply noise or this DIDT impact can be further optimized. We have some proposal of doing tri-state buffer, using the tri-state buffer. These are part of research which one has to do. And this is the entire actually project which is sanctioned by DST SERB, where some students are designing this phase lock loop block. This is the entire VFC module which I have discussed. You have seen P2, P1, P0 here, but this P2, P1, P0 has to be controlled externally. For that, ADC has to be designed. And then this section is nothing but the clock tree, the proposed clock tree, which I was discussing, that we need to work on it. Clock getting, which we have done, and then application section. Till now, I have discussed integration of VFC with the clock getting. Here it will be integration of VFC with the clock tree, proposed clock tree, then proposed clock tree will be connected with clock getting, and then you can apply. Then the performance may be much better comparing to the result what we have obtained. Okay. So that's all from my side. I'm open for discussion if someone has any query.
If you have any queries, please raise your question. I think there will be no question for you, sir.
Okay, fine. I think
Okay.
then I think it is good to stop the presentation now.
Okay, sir. Sir, my sincere thanks for your presentation at this faculty development program. And your insights and expertise made a significant impact, and we are grateful your valuable speech. Thank you again, sir, for your sharing knowledge and sparing your precious time for us. Thank you, sir. Thank you.
Thank you, Ms. Sutradhar, for inviting and allowing me to give a talk. I think I'm sure there may be quite a few faculty members also available over here. If anytime any of them are interested to get connected with me, I'll be open for discussion. And secondly, just in this forum, I'm just telling that there are quite a few vacancies are also available. We have advertised, few advertisement will also come up. If any of your students who are completing their graduation or they have passed out last year, who has basic knowledge of VLSI, they can definitely contact with me or connect with me. Thank you.
Okay, sir. Okay, thank you, sir. Thank you, dear participants. We will meet again tomorrow at 10:30 a.m. Thank you.